Today's AI agents have a strange blind spot. They can walk into a completely new, complex problem and solve it on the first try. But hand them the same kind of task 10,000 times, and they might still make the exact same mistake on attempt number 10,001. Learning from experience, actually getting better over time, is quickly becoming one of the most important capabilities an agent can have. This is about how to build that capability, not by hoping the model magically learns on its own, but by engineering a system around it that learns reliably. The capability paradox. Here's the core problem. Once a model is deployed, its parameters don't change just because it had a conversation. Everything it figures out mid-task, adapting to context, remembering what happened 5 minutes ago, disappears the moment that task ends. It doesn't carry over to tomorrow. And here's the trap. Just because a system saves a transcript of what happened doesn't mean it learned anything from it. A pile of saved conversations is not the same thing as a lesson. Raw logs are messy. They mix genuinely good strategies with lucky accidents, wrong guesses about what caused success, and even untrustworthy input from the outside world. Preserving experience is not the same as learning. From it dropping 100 old transcripts into a database doesn't make a system smarter. It just makes those transcripts searchable. Real learning requires 4 active steps. Evaluate what happened, compare it against other cases, generalize a pattern, and validate that the pattern actually holds. There's also a useful distinction to draw here. One kind of memory captures what the user is like and what the world is like. What we're talking about here is different. It's capturing what to do, and under which conditions. One makes a system more informed. The other makes it more skilled. Why not let the model train itself? You might ask. Why not just let the agent update itself continuously after every task? Because production environments almost never hand you a clean signal. A user being satisfied doesn't mean the rules were followed. Test passing doesn't mean the code is correct. Sometimes it just means the failing test got quietly deleted. And even a small local update to a model can cause it to forget things it used to know, drift away from its original behavior, or become less safe. If a live system is allowed to update itself based on unverified feedback, errors, and even malicious instructions smuggled in through content it reads, can get baked in and repeat themselves over and over. The engineering path. So if the model itself can't safely learn on its own yet, the solution is to build learning as a system around it. That system has a loop. Record what happened. Verify whether the outcome and the process were actually correct. Look across many examples to find real patterns, and only then decide what to update. Critically, nothing goes straight into production. Every proposed change becomes a candidate first, and it has to pass regression tests and safety checks before it's allowed to affect real behavior. Learning signals start with evaluation, not summarization. If a system can't tell the difference between success and failure, then any lesson it writes down is really just a guess dressed up as insight. Some tasks are easy to check. Did the tests pass? Did the refund actually process? Does the order status reflect it? That's ground truth from the real environment, and it's far more trustworthy than the model's own account of what it did. But a correct outcome doesn't guarantee a correct process. You can make tests pass by deleting the ones that fail. And telling a customer you'll be refunded in 7 days can make them happy in the moment, even if nothing was actually submitted. For tasks with no single right answer, tone, judgment calls, you need a structured rubric, evidence for every score, and an explicit "I'm not sure" option instead of a vague overall grade. 3-layer trajectory verification. Think of verification in 3 layers. At the bottom, the outcome layer asks a simple question using hard evidence. Tests, database state, tool results. Was the task actually completed? In the middle, the process layer checks whether it was done the right way. Were policies and permissions respected? Was the sequence of actions appropriate? At the top, the quality layer judges things that are harder to formalize. Was the language appropriate? Was the strategy sound? And that's the one layer where a language model judge, guided by a clear rubric, actually makes sense. The rule of thumb: rely on hard evidence wherever you can get it, and only hand the fuzzy, subjective judgments to the model. A real rubric. Customer service agent. Here's what a real evaluation rubric looks like in practice. Was the core request actually resolved? Were any policies or permissions violated? Was anything disclosed that shouldn't have been? Are the claims backed by real evidence? Was the language natural, not repetitive? And when the original ask couldn't be granted, was a lawful alternative offered instead of just a flat refusal? The standout item here is checking whether what the agent claimed to do matches what it actually did. Cross-referencing, "I've submitted your refund," against the real tool call and the resulting account state. A simple summary of the final message would never catch that mismatch. 4 ways to encode a lesson. Once you know something went wrong, where do you actually put the fix? There are 4 options. A knowledge base, good for facts, exceptions, and anything you want to look up on demand. A prompt or a skill, good for judgment principles and procedures you can clearly state in language. Program code, good for anything deterministic that needs to run the same way every time. And model parameters, reserved for things too high dimensional to write down, like perception or writing style. The rule for choosing between them isn't how long the lesson has been true. It's whether the capability can naturally be expressed in that medium. In practice, a single sophisticated agent usually uses all 4 at once. Method 1. Consolidating experience into knowledge. The lightest touch form of learning is turning repeated experience into a written knowledge document. The process runs in layers. Keep the raw, unedited trajectories for auditing. Produce a short analysis of each individual run, and only after comparing many similar runs do you write a formal, forward-looking document, one that states when a strategy applies, what to avoid, and what the supporting evidence is. The discipline that matters most here: a single lucky success should never become official policy. A pattern only earns its way into formal knowledge once it's backed by multiple independent, non-failed examples. Method 2. Encoding experience as instructions. Some lessons are best captured as an instruction rather than a reference document. Rules that apply almost everywhere belong in the core system prompt. Narrower, domain-specific procedures belong in dedicated skill files. Think of this as leaving a note to your future self. Next time this situation comes up, try this first. The discipline that keeps this from spiraling out of control. Generate a small, targeted edit from a cluster of similar failures, rather than rewriting the whole instruction set from scratch every time. And test any new rule 2 ways. Does it actually fix the failure cases, and does it avoid breaking the old cases that used to work fine? A rule meant to stop unnecessary escalation, for instance, has failed if it also stops the agent from escalating genuine emergencies. Method 3. Encoding experience as programs. When an action is stable, repeatable, and easy to verify, it's wasteful to make the model reason through it step by step every single time. Instead, compile it into a small program. The process: capture the first successful attempt in detail. Replace the specific values with parameters so it can be reused. Add checks before and after every action. Validate the whole thing in a reset test environment. Then let future tasks match against it and run it directly. No model calls needed. If anything about the environment changes and a check fails, retire that version immediately and fall back to full reasoning. This kind of compiled workflow can run many times faster than reasoning it out, fresh each time. But there's a critical warning here. Just because every button got clicked doesn't mean the task actually finished. You always have to verify the real end state. not just that the actions ran without error. Self-modifying harness code. Sometimes the fix isn't a rule or a document, it's the underlying system code itself. This still isn't the agent quietly rewriting itself live. It's treated as a real software release. Propose a change, explain the evidence behind it, predict what should improve and what might break, then test both predictions before anything ships. And the agent generating that proposed fix should be given more than just the failure. It also needs to know what behavior must be preserved and which similar fixes were already tried and rejected, so it doesn't keep proposing the same broken idea over and over in different words. Method 4. Encoding experience in parameters. Some capabilities are just too high-dimensional to write down as a rule or a document. Recognizing patterns in an image, producing natural-sounding speech, planning many steps ahead. Those need to be trained directly into the model's parameters. Note that the deciding factor isn't how long the capability has been stable. It's whether it can be represented externally at all. Verified interactions become training data. Good examples for supervised fine-tuning, comparisons for preference training, and reliable reward signals for reinforcement learning. And even after training, you still have to check whether the update accidentally made the model worse at things it used to be good at. Beyond artifacts, updating the update method, there's a second, deeper question beyond just, where do I put the fix? Are you optimizing the content of a specific rule or document, or are you optimizing the process that generates and manages those rules and documents in the first place? That process can be improved at increasing scales. A single rule, then the whole structured context, then a full workflow, then the underlying system code, then even the logic that proposes candidate changes in the first place. The safest default is always the smallest, most local change. It's easier to trace and easier to undo. One clever trick worth mentioning. Instead of repeatedly asking a model to rewrite an entire block of instructions, which quietly erodes rare but important details over time, treat the instructions as a set of individually addressable entries that get merged and deduplicated instead of rewritten from scratch. Only zoom out to bigger, riskier changes when small local fixes keep failing to solve the real problem. The dual loop architecture, put it all together and you get two loops running side by side. An online loop that just does the work and records what happened. It never rewrites the live system directly. And an offline loop that gathers up all that recorded evidence, diagnoses what went wrong, proposes fixes, validates them, and only then releases a new version. A great real-world proof of this idea comes from an agent operating inside a video game. It picked its own next goal based on what it already knew how to do, built a library of validated skills, and combined them to tackle harder challenges over time. None of the three pieces work alone. A skill library, without a sense of what to learn next, just wanders aimlessly. Self-reflection without real environmental checking lets errors pile up, and exploration without anything being saved means starting from zero every single time. Diagnosis, validation, release, rollback. When something breaks, find the smallest fixable cause. Don't over-correct based on thin evidence. And there's a subtlety worth understanding here. There are actually two separate capabilities being tested. Can the system produce a genuinely good fix? And separately, can the agent actually find that fix and use it correctly once it exists? A perfectly good update is useless if it never gets loaded at the right moment, or if it gets loaded but isn't followed properly. One clean way to tell these apart: hold the fix constant and swap out which model is doing the actual task. If a stronger model benefits from the fix, but a weaker one never even finds it, the bottleneck is retrieval, not the fix itself. Where verification breaks down. This whole approach works best when feedback is fast and objective. Code either runs or it doesn't. A database state either changed or it didn't. Open-ended work like research is a different story. Feedback is slow, there's often no single right answer, and the things that actually matter, good judgment, long-term value, are hard to score in the moment. A real test of this, running several attempts at turning a research idea all the way into a finished paper, most of them failed partway through. The failure patterns were telling, retreating to a familiar, easier approach once the real one got hard, getting overly convinced that noisy results are meaningful, and simply not knowing which anomaly is worth chasing or when to give up on a bad idea. The fix isn't a smarter model, it's better bookkeeping, separate claims from the evidence behind them. Keep a permanent record of failed attempts instead of only surviving successes. Keep a diverse pool of options alive instead of collapsing onto the first thing that scores well, and make sure a human is still shaping the questions being asked, not just approving individual actions. Safety boundaries for self-evolution. Letting a system modify itself over time raises the stakes on a single mistake. Anything read from the outside world, a web page, an email, a tool's output, has to be treated as untrusted evidence, never as an instruction to follow, and never something that gets promoted directly into a permanent rule. New capabilities always sit in a sandbox area first, going through security and regression checks before they're allowed anywhere near real traffic. And here's the one boundary that can never be crossed. A system is allowed to modify its own instructions, its own skills, even its own tools. But it must never be allowed to modify the tests, thresholds, or audit logs that decide whether its own changes get approved. Otherwise, it could make a regression look like an improvement just by quietly lowering the bar it has to clear. Sleep learning. Consolidation and forgetting. Think of this as a background consolidation process. Not something that literally has to run at night, just something that happens periodically. Separate from live operation. The cycle. Trigger when there's enough new evidence. Review what's currently known. Collect and merge new signals, preferring small local patches. Validate the proposed changes against safety and regression checks. And finally, prune anything outdated or unused. Without this step, things quietly rot. Documents start contradicting each other. Instructions balloon with dozens of edge case exceptions, and duplicate rules pile up doing the same job under different names. A smart detail worth borrowing. Take a snapshot before consolidating. So if an automatic merge goes wrong, you can roll it straight back instead of living with the damage. The big picture. Models can't yet reliably learn from experience entirely on their own, so the practical path today is to build a verifiable learning system around the model instead. Pull signals from evaluated, real interactions. Route each fix to whichever medium actually fits the capability. A document, an instruction, code, or the model's own parameters. Always prefer small, traceable, reversible changes over sweeping rewrites. Keep the system that does the work completely separate from the system that learns from it, and never let a change reach production without passing through validation first. And for genuinely open-ended goals, people still need to be in the loop, defining the problem and deciding what good even looks like. Discussion questions. A few questions worth sitting with. If a lesson has 3 successes and 1 failure tied to a newer version of something, has the lesson gone stale, or does it just need a narrower scope? If customer satisfaction goes up while rule violations also go up, why can't satisfaction alone be trusted as a signal? And what guardrails would catch that? The same underlying bug can often be fixed with an instruction, a code-level check, or a training update. What evidence would tell you which one to reach for? How do you draw a hard line between the parts of a system an agent is allowed to change and the parts that must always stay out of its reach? As a knowledge base grows, retrieval mistakes and conflicting entries can start to cancel out the benefits of learning. How would you version, freshen, and retire that knowledge over time? And finally, If you were designing this for something high stakes, like medical customer service, how would you split responsibilities across parameters, knowledge, skills, and hard code constraints?